Hey everyone, welcome to the final video in our series. Now today we are talking about similar triangles once again, and we're going to do in this video a few questions in which first we prove two triangles are similar, and then we're going to use these ideas to apply similar triangles to solving some problems, some real world problems. So let's jump straight into some questions, because in the previous video I covered all of the similarity tests and everything you need to be able to prove two triangles are similar. So let's jump straight in with a couple of questions in which we're going to revise what we looked at in the previous video, as well as learn a couple of new things in terms of application. All right, now, don't mind these badly drawn triangles, but here we have these here, A, B, C, D, E, and we want to prove that this triangle is similar to this one down here. Now, as you remember from congruence and similarity, when we write out these proofs, we kind of want to structure this like a paragraph, like an English paragraph, if you remember me saying before. So first of all, we're going to give an introduction. We're going to introduce our two triangles. So we are saying in triangle ABC and triangle EDC, we want now, after we've introduced these two, to actually give reasons for similarity. So these can be corresponding angles that are equal or sides that are to a similar scale. But we see here that we haven't really been given any side lengths, so we immediately want to look for some angles here that we can say are the same. So it's not immediately obvious, but we can use some things we've learned previously from angle geometry. Now we can say that because we have two parallel lines here, and we have a transversal, another line cutting through those, we get a couple of angle relationships happening. Now if we look at the shape of this, we can see that from our previous work on angle relationships that these two are going to be the same. They're equal. These are what we call alternate angles. So I'm going to write that as a reason. So angle ABC is equal to angle EDC. Why? Well, these are alternate angles of parallel lines. And we can write that as AB parallel to DE. Okay, so that's one reason. We have a pair of alternate angles, but we have another pair here of alternate angles. So I can say that the angle BAC is equal to DEC. So I can say that they're equal for the same reason. So I can say angle BAC is equal to DEC, and that's for the same reason. So I'm putting these little quotation marks here. Now remember, with similarity, all we need to do with angles is we only need to prove 2 out of the 3, because if 2 angles are equal in a triangle, because all triangles add up to the same amount of degrees, the third pair are also going to be equal. But you can see you didn't have to do just both alternate angles. You could have also said that, well, this is equal to that because they're vertically opposite angles. So we could have gone through with that thing as well. But because we found two corresponding angles in the two triangles that are equal, that is enough to say that they are similar. So I'm going to write a concluding statement. So I'm going to write, therefore, triangle ABC is similar. Remember, similarity we write with these three vertical lines, is similar to EDC. And we can either write angle, angle, or we can write two pairs of equal matching angles. But I'm just going to write angle, angle here. So that is enough to prove that these are similar. Now let's try another question. Once again, proving similarity. I'm going to draw this triangle here. I have, oops, E, A, and I have this triangle here, D, B, C. All right. This length is 4 from B to C. This length is 18. This length is 6. And this length is 12. Okay, now, this is a lot to unpack because you can see that my two triangles here are actually in different orientations. This one in green is a different orientation to this one in pink. So what that means is that because they're in a different orientation, this is not actually the corresponding side to this one up here, nor is my side BC a corresponding side to this one here, because they're all in a different orientation. So what I'm going to do is I'm going to take my little triangle here and I'm just going to flip it around a little bit so it's in the same orientation, and that's going to be able to tell me which sides are corresponding to one another. So what I'm going to do is I'm going to keep my original picture because that's going to help me with another part of my question, but I'm going to redraw these in as two separate triangles. Often when you get questions like this where it looks a little bit hard and strange to kind of get your head around, I try to separate them and then work through them one by one. So what I'm going to do, I'm going to transform this one. If we think back to last year's content with our different types of transformations, so I'm going to just rotate this. So I'm going to rotate this so it is in the same orientation as my big triangle. And the side down here is going to end up being 6, and this side is going to be 4. Hopefully you can visualize that by, if we rotate this a certain amount, say this way, my 6 is eventually going to be on the ground, on the horizontal surface, and then my 4 will end up over here, but now I've just reflected it so the 4 corresponds to the 12 here. So pause the video, have a go at doing that rotation and reflection if you'd like, but I'm basically just drawing these now so they are in the same orientation, and this is going to help me to work with actually proving for similarity. Now, we said in the previous video, for two triangles to be similar, the scale factor from this to this must be the same as the one from here to here. So we're going to test that quickly. So, First of all, we're going to introduce our two triangles in triangle ACE and DC. Whoops. CB. I want to do some calculations to check these scale factors. Now, sorry, I should have actually labeled these here. So that's AC, and this thing here is DC, and I have B and E. Okay, this is going to be a lot easier to work through now. So I want to check the scale factor. So I'm going to first look at the ratio of AC to DC. So AC over DC equals to 18 over 6. And that equals 3. Now I'm going to check another one here. I'm going to check EC, this one here, over B. Oops, sorry. I have these the other way around. This is D, this is C. I'm going to check EC over BC here. So EC as a ratio over BC equals 12 divided by 4, which once again gives me 3. So I have two corresponding sides which have the same scale factor, and I need one more piece of information. Now it's a bit harder to see with this second image, so I'm going to go back to my first one, and if you guys notice here, I actually have a common angle, because this, let's do it in this color, this angle here, this vertex, this is an angle in both my larger triangle and my smaller triangle. So I can say that it is common. So I'm going to write here for my final bit of reasoning that ACE equals to angle DCB, and I can just write that it is common. This is a common angle. So now I have 3 different reasons for the similarity with these two triangles. So what I'm going to say here now is my concluding statement. So I'm saying therefore ACE is similar to angle DCB. And I can say that the sides adjacent, remember adjacent just means next to, sides adjacent to equal angles are in proportion. And remember the in proportion here means that the scale factor is the same. So the sides are scaled the same way. They're in proportion. And that is how we can go about proving similar triangles. Now let's look at one more question in which we are going to take what we've done and apply this. So in this question, I'm given that Chris's shadow is 1.2 meters long, while a 1 meter vertical stick has a shadow .8 meters long. And there's a couple of things we want to do. So part A, we want to prove the triangles are similar. And this is going to make more sense once I actually draw the picture. Similar. And in part B, we want to determine Chris's height. Okay, so I'm going to draw Chris here with some unknown height, and he is casting a shadow of 1.2 meters. And let's do this in another color. I can see that with my weirdly drawn Chris with a long neck, looks a bit weird, but his height with the horizontal ground with just some imaginary length between this point on the end and the top of his head makes a triangle. And because he is standing kind of vertically upright and the ground is horizontal, he makes a 90-degree angle with the ground. Now this will usually be given in your questions anyway. And I have this angle here. And I have a vertical stick here that's 1 meter high. And I have the ground in which this casts a 0.8 meter shadow. And I have made this triangle with that as well. Now, in the question, you're given that these two angles are equal, and the stick is vertical, whereas the ground's horizontal, so the angle is going to be 90 degrees. Same with Chris over here. Okay, so now we want to actually see why these are similar. Now, this is actually not too tricky because all the stuff we're already given in the question. You can see that I have a 90-degree angle in both triangles and another equal angle in both triangles. So I have two matching angles that are equal. That means the third angle will also be equal. So I already have all of the information here. So to say they are similar, we just have, for part A, we have two pairs of matching angles. And that's given in the question. So, remember, all we need is two angles to say that are equal, to say that two triangles are similar. And for part B, we want to now actually find Chris's height. Let's call that h. All right, now, because these two triangles are similar, that means that whatever the scale factor is between my 1.2 meters and my 0.8 meters, that will be in proportion to Chris's height and the 1 meter stick. So to find out his height, we're going to first have to find the scale factor. So the scale factor equals to, let's do the bigger length over the smaller length. So the scale factor equals 1.2 divided by 0.8, and that gives me 1.5. That's my scale factor here. But now, because we've already proved that these two triangles are similar, that scale factor of 1.5 is going to be the same scale factor for h to my 1 meter here. So therefore, because scale factors are the same for all corresponding sides of similar triangles, That means that my scale factor is going to be equal to Chris's height h over 1. And I already know my scale factor, that's 1.5, equals to h divided by 1. Now, h divided by 1 just gives me h, or we can get rid of the 1 also by multiplying both sides by 1 to solve this equation. And multiplying 1.5 by 1 just gives me 1.5. So Chris's height is going to be 1.5 meters high, because the scale factor 1.5 is the same for all of the sides of my similar triangles. So it's going to be the same for my 2 pink lines that I've highlighted, my 2 green ones that I've highlighted, and also the 2 orange ones that I've highlighted. That's the thing with similar triangles. All sides have to be in proportion. But that is how we can prove for similarity as well as apply it to some questions concerning real life applications and problems. But thank you so much for joining me in this series, guys. I will see you in the next one.